Welcome back. So here we are, chapter 5. So chapter 5 is going to cover molecules and compounds. You came from chapter 4 understanding the atom, what the atom is made of, protons, neutrons, and electrons. You know about the valence electrons. And now we're going to take those atoms and we're going to bring at least two of them together so we can have a molecule. And a molecule is nothing more than two or more atoms bonded together. It could be the same type of atom or it could be different atoms. But if it happens to be different atoms, we also call them compounds. If there happens to be more than two atoms but the same element, we call it a molecular element. So these are the concepts we're going to discuss on this chapter. We're going to see what the law of constant composition is. We're going to learn how to write chemical formulas, what element should go first. We're going to see a formula. We're going to be able to count how many atoms of each element you have. Then we're going to see that based on the position of the periodic table of the elements of the compound, it can be an atomic or it could be a molecular compound. And then we're going to reclassify more on a deeper level as ionic or molecular compounds. And then we're going to see how we can write formulas for ionic compounds. Briefly, we're going to talk about what common names are. And then we're going to start using what we call the UPAC system, the International Unit of Pure and Applied Chemistry, which is the organization that set up the rules. And we're going to see how we're going to name compounds that contains two elements, binary, with only one type of ion, and you already learn what an ion is, positive or negative, and one that can have more than one type of ion. Then we're gonna get introduced to the polyatomics, and then we're gonna go into finish naming the ionic compounds, and we're gonna move into naming the molecular compounds, and we're gonna learn about a special type of compounds, which are gonna be the acids. And they're going to be binary acids, they're going to be oxyacids or polyatomic acids. And depending on what we learn about the polyatomic ions, then we're going to have to use that to be able to name the acids. And then we're going to, in preparation for chapter 6, we're going to learn how to calculate the molar mass or the formula mass of a compound. So let's begin. Let's start with the law of constant composition. What is that? Well, let's start with this example. On the left side, we have hydrogen peroxide, and I'm going to tell you that the formula for hydrogen peroxide is H2O2. On the right side, you have a very common compound, which is water, H2O. And the point I'm trying to make here is that both substances, the hydrogen peroxide and the water, both of them contain only hydrogen and oxygen. And I can tell you for sure that you can drink the water and you will not die. But if you drink the hydrogen peroxide, that's a whole different story. So even though they have exactly the same elements, they're very different. And the reason is their proportion between the elements. You can see that you have on hydrogen peroxide 2 hydrogens for every 2 oxygens, basically 1 to 1. While on the water, you have 2 hydrogens for every 1 oxygen. So the composition of each, even though it has exactly the same elements, is different. Therefore, they're different compounds. And we know that. We can see the formulas. We know the effects and their physical properties and everything. So if we try to simplify that more, if I have, for example, 34 grams of hydrogen peroxide, what I'm going to have is a proportion of 60 grams of oxygen for every 1 gram of hydrogen. Or 32 grams of oxygen for every 2 grams of hydrogen. So that's the proportion we're gonna get all the time whenever we have a sample of hydrogen peroxide. 60 grams of oxygen for every 1 gram of hydrogen. In the case of water, the proportion is different. You got 8 grams of oxygen instead of 16 for every gram of water, of hydrogen, sorry. So once more, they have a different composition. So how we can use that on a problem like this? So we know that for water, the ratio between oxygen and hydrogen is 8 to 1. For hydrogen peroxide is 16 to 1 oxygen to hydrogen. So if I were to fill up a table like this, I know that my proportion for oxygen to hydrogen on water is 8 to 1. And I'm given the mass of oxygen, which is 55.0. And I've been asked to find out how much hydrogens I would have, so it keeps the proportion that it should keep. So it's basically a problem like this. I know that the proportion of oxygen to hydrogen is 8 to 1. I know how much oxygen I have, 55, and I'm looking for how much hydrogens I would have. Since we're talking about water, it doesn't matter how much water I have, the proportion is always the same. That's why I can say that they're equal, and that allows me to find the unknown. So this is going to be x equals 55.0 divided by 8. So let's see how much is that. 55.0 divided by 8. That's going to be 6.88 grams. So we will have, for every 55 grams of oxygen, if we're talking about water, we will have 6.88 grams of hydrogen, which means the total mass of this water, if we have 55 grams, is going to be 61.88 grams. This plus that. What about the next one? The next one, we're doing it for hydrogen peroxide. And we know that oxygen, for hydrogen peroxide, oxygen to hydrogen is going to be 16 to 1. However, we're not given the oxygen, we're not given the hydrogen. The only thing we're given is the total mass. So how can I do that? Well, I know the proportion of oxygen to hydrogen, but I do not have oxygen, I do not have hydrogen, so that doesn't help. However, I know that you will have altogether 17 grams of hydrogen peroxide for every 1 hydrogen. So the hydrogen peroxide altogether to the hydrogen is going to be 17 to 1. So how do I do that? So 17 is going to be corresponding to the total mass, which is 135. The hydrogen is 1, and I do not know the hydrogen here. So once more, the question mark is going to be 135, once I do my algebra, right, divided by 17, which is going to be, let's see how much that's going to be. 135 divided by 17 equals 7.94. So that means, since I was doing the total mass to hydrogen, that means I just found my hydrogen, which is 7.94. And since I know the total mass, So this is the total mass, and I know how much hydrogen I have. The difference should be my oxygen, right? So I'm gonna have 128.1. So basically all I done is just refer to any of the proportion between the two elements or the one element to the total mass, and using algebra I can find my proportions just because the law of constant composition tells me that when I have a compound, it doesn't matter how much total mass I have, the proportion of the elements is always the same. So with that in mind, go ahead and do your first daily work. So you're basically doing what I just did, just fill up the table. So leaving that concept behind, let's do two concepts. We have to do these two simultaneously for them to make sense. How are we going to write chemical formulas? How are we going to determine the total number of each type of atom in a chemical formula? So at this point, we're assuming you have never seen this before, so we're going with the baby steps, the basics. So let's do this problem. And you're going to need to have a periodic table close by. Never leave home without it from now on. So write chemical formulas for compounds containing A. What do we have on A? 3 iron atoms. So we're going to have 3 iron atoms and 4 oxygens and 4 oxygens. So how do we write the formula for that? Well, the first thing we're going to do is you learn on chapter 4 that the periodic table is divided by this set of steps in here, and to the right you're going to find your metals, and to the left you're going to find the non-metals. So that's the first thing you have to remember. So what does that have to do with writing these formulas? Well, we have iron and we have oxygen. Do we write it like this or do we write it like that? So there's a system. This is a very systemized procedure, so everybody all across the world can understand each other. It doesn't matter the language you speak, as long as we speak the language of chemistry the same. And the rule is the first element is the one that is more metallic. So between iron and oxygen, which one is more metallic? We know that iron is a metal, but that's not what I'm saying. So the metals are on this side, so this is the more metallic, the one more to the left. So the iron will go first, followed by the oxygen, and we are told that you have 3 iron atoms, so we're gonna represent that with a subscript. So this number of front is what we call a coefficient. We're not ready for that yet. We're gonna see that later. Right now we're talking about just the formulas. So the number of atoms is given by a subscript right after the element. And we have 4 oxygens. So that would be how we write that formula. So a new concept that we just learned, the first element that you write is the one that is more to the left, the more metallic one. So the first one will be Fe3O4. The second one is going to be phosphorus and chlorine. Phosphorus is there, chlorine is there. Which one is more to the left? Phosphorus is more to the left, so phosphorus will go first. Chlorine will go after. We have 1 phosphorus and 3 chlorines. But in chemistry, we do not show the 1. If you don't see a number, we assume it's 1. So no need to put the the 1 in there. Another one phosphorus. Actually, it's the same one. I don't know how that happened. The next one, 2 silver atoms. So we're gonna have silver, which is right there. The more you use the periodic table, the easier it will be for you to find those elements. So we got 2 silver atoms and oxygen. Silver is more metallic, so 2 silver atoms and 1 oxygen. 2 chlorine atoms and 1 magnesium atom. So chlorine is right there. Magnesium is right there. Definitely magnesium we have to go first, right? It's more to the left. So we have 1 magnesium and 2 chlorines, and we put a subscript indicating the 2. And the last one is bromine, which is right there, and carbon, which is more to the left. Carbon is more to the left, so it's going to be followed by bromine. And we have 4 bromines and 1 carbon. And that's how you do the formula. So once more, the element that goes first is the one that is more to the left. The number of atoms is denoted by a subscript that we put right after the element. So go ahead and do that. That's your second daily work. Moving forward, let's do some more of what we just did. So now what we're going to do is, by looking at the formula, we're going to figure out how to count how many atoms you have of each one. So the first question here is the number of this unit. So the whole unit, how many do we have on the first one? According to what we just learned about the way we write formulas, so all this here is followed by a number 2. The reason for those parentheses is so it doesn't look like a 22. That tells us everything in the parentheses, we have 2 of them. So number of, we call that acetate units. There's gonna be 2. Let's continue the column going down. On this one, there's no parentheses, so there's only 1 of those. So all this is what we're looking at. And this one, we're gonna have 4. So that would be 4. Number of carbon atoms. The only carbon I see is this carbon there. So but that carbon is inside the parentheses, and everything on the parentheses gets multiplied by 2. So inside the parentheses, we have 2 carbons, but we're gonna have 2 of those groups, so this will have to be 4 carbons. On the next one, there are only 2 carbons, and on the last one, you have 2 inside the parentheses, but everything inside the parentheses is multiplied 4 times. So altogether, you're gonna have 8 carbons in there. Number of hydrogen atoms, the same story. Now we're looking at the hydrogen. So we're gonna be looking at that 3, and that 3. On the first one, On the first one, it gets multiplied by 2. So that's gonna be 6 of them. On the second one, there's no parentheses, so you just have what you see, 3 of them. And on the last one, you have 3 inside the parentheses, but you're gonna have 4 times the parentheses, so that should be 12. Number of oxygen atoms. Oxygen is inside the parentheses also, multiplied by 2, will be 4 on the first one. There's 2 there, and there's no parentheses, so just 2. And there's 2 more there, but it's 4 times the parentheses, so that would be 8. number of metal atoms. Which one are my metals? These ones over here, right? Except the hydrogen. So those are going to be my metals. So let's see. Do I have any of those in here? On the first one, yes. I have magnesium, and there's only one of them. On the second one, I have sodium, and there's only one of them. This number outside the parentheses only applies to whatever is inside the parentheses. And on the last one, I have chromium, and there's two of them. And that's how you will fill up this table. So let's practice some. So that's your daily work. And with that, now you know how to write chemical formulas. The element that is more to the left always goes first. The amount of atoms is given by a subscript right after the element symbol. And that's what we just finished doing. Two more concepts. Classify elements as atomic or molecular. Classify compounds as ionic or molecular. So I told you before that a molecule is two elements or more combined. So if I have this bonded to that would be a molecule. If I have this bonded to that, bonded to that, bonded to that, that's a molecule. If I have this, that's not a molecule because you need at least two or more combined to be a molecule. So that's just an atom. And what about when I have something like this? And those are representing different elements, obviously, right? So that would be a molecule. It still fits the molecule definition, two or more atoms together. However, they are different, so we're going to say that this is a compound also. This one here, or this one here where they are the same, is not a compound because they have to be different. So this still is an element, but it's a molecule also, so it's a molecular element. So that's the kind of a basic concept so far for the first part. So let's see something else. So here's the classification that we are being carrying since chapter 3. Pure substance. We're not talking about mixture, only pure substance. Pure substance are either going to be elements or compounds. The elements can be atomic. For example, one lithium combined with another lithium, with another lithium, with another lithium. That's going to give you a chunk of lithium, which is a metal. So that would be atomic because you have the just atoms. But what about something like this? Oxygen combined with oxygen. The actual formula is something like this. We're going to learn about this later. So it's a molecule because there's two of them or more, but they are the same. So it's a molecular element. So that's the difference. So when you have the elements by themselves, not bonded, like on metals, it's an atomic solid. When you have it bonded, then we're talking about a molecule. So elements can be by themselves, or they can be combined with other elements of themselves. That would be a molecular element. If they happen to be different from each other, this one and that one, then they're compounds. And they could be molecular. Molecular would be when you have a non-metal combine it with another nonmetal, like water. Water, H2O. This is a nonmetal. This is a nonmetal. So this is a molecular compound. So quick review once more. It's a compound because the elements are different. And it's a molecular compound because both elements are nonmetals, which are going to be the ones on this area here. So let's put that to practice. Let's do this problem. Classify each element as atomic or molecular. There's something else I need to tell you. And how many, I know that a lot of you have a smartphone, and your smartphone could be an iPhone. There's a high possibility that you have an iPhone. I want you to find the iPhone in the periodic table. As you saw in the video last week on the discussion, the iPhone or any smartphone is going to have a bunch of almost over 83 elements from the periodic table. That's not what I'm talking about. I want you to find the iPhone. So I go all the way up, fun. So once more, I go all the way up and fun. Those elements that I just highlighted for you, those elements in nature, they are never by themselves. In nature, you never find oxygen by themselves. You always find O2. Chlorine, in nature, you never find chlorine by itself. If you don't find it within a compound, then it's going to be Cl2. We call this the diatomic elements. So all these elements are going to be doing that in addition to hydrogen. So you never find hydrogen by itself, you find H2. And there's a few more over here that you also find like that, but the ones I want you to focus on are the ones that we are 100% sure that they are, and they follow a pattern. So if you're trying to classify an element as atomic or molecular, if it's molecular, then it's one of those. Anything else would be atomic. So let's put that into practice. Chlorine, like I said before, fun. Chlorine is there, so chlorine will be molecular. Argon is not in there, so that would be atomic. Cobalt is not in there, atomic. And hydrogen is the other one I told you, is the iPhone and the hydrogen. So that would be molecular. What about classifying a compound? So we're not talking about the element anymore. Now we're talking a compound, two or more different elements together, as ionic or molecular. To be ionic, you're gonna need a metal combined with a non-metal, and that's the division you're gonna get right in there. Anything to the left is a metal, anything to the right is a non-metal, except the metalloids that are touching the steps. So, and if you happen to have a non-metal combined with another non-metal, then you have a molecular compound. So let's do that. First one, carbon and sulfur. Two nonmetals, so this is a molecular compound. Copper, that's a metal, and oxygen, that's a nonmetal, so that will be ionic. Potassium iodide, that is a metal, that is a nonmetal, so this one is also ionic. Phosphorus trichloride, phosphorus is right here, a nonmetal. chlorine is there. So 2 nonmetals, so this would be molecular. As simple as that. Based on what you learned on chapter 4, now you can apply it to find out which type of compound you have. So let's go ahead and do that daily work. And we're gonna stop here for right now. So once you do that daily work, when you come back, we will be doing chapter 5, part B. So until the next time, see you later. Take care.